Hey there. In this short video, we're going to do one more example where we analyze the graph of a function using the first and second derivatives. So the same kind of directions. I want to find the intervals of increase, decrease, the local extrema, concavity, inflection points, asymptotes. Here, the function I've chosen for this example is a rational function, x squared minus 4 over x squared plus 4. It's defined for all real values of x. X squared plus 4 is never 0, but it clearly has an asymptote. We can actually start by taking care of that right away. I also want to label, I haven't been talking about intercepts for these functions, but if you make a sign diagram for the function itself, here I'm just going to factor this numerator into x minus 2 times x plus 2. The denominator, again, is never 0. It can't factor. X squared plus 4 is an irreducible, non-factorable polynomial. But that gives us a little bit of information about these intercepts. One of them is happening where x is positive 2. The other one is happening where x is negative 2. And to answer that asymptote question, let's do it first this time. We can just use this space. So we can take the limit as x goes to, for a rational function, it'll be the same, positive or negative infinity. And that skill you developed back in chapter 2 is going to come in handy right now. This thing is a rational function. It's degree 2 polynomial over degree 2 polynomial. So you can divide everything by the highest power of x squared there, and do the algebra, but it'll always turn out to be the ratio of the leading terms. In this case, it's going to be 1 over 1 or 1. Yeah. So y equals 1 is the equation of our horizontal asymptote. All right, so what remains to do in the analysis? Well, the intervals of increase and decrease. We can see again in the graph a lot of this information. It looks to me like this graph is, because we read the inputs left to right, it looks to me like this graph's outputs are decreasing until x gets to, well, it looks like 0. Yeah, and by the way, that's the y-intercept. If you calculate f of 0, in this formula up there, you'll get 4 over 4, you'll get minus 4 over 4, so you get negative 1. So the y-coordinate of the y-intercept there is negative 1. And then it looks like the function starting at x equals 0, its outputs increase from there. Yeah, so you can kind of see that from the graph. Let's just have the first derivative and its sign diagram confirm that for us. But what's not clear is exactly where there are these inflection points. I see that the graph is concave down. It's concave down until somewhere around in here, and then it switches to concave up. Yeah, so I think there's an inflection point there and an inflection point there, and the calculus can tell us precisely where they are. All right, so let's get busy. We have to take some derivatives. It's going to involve some quotient rule and some algebraic simplification. So I'm going to scroll up here. I've got the function written again so I can look at it while we're differentiating. And I'm going to start by taking the first derivative, because my goal is to have two nicely organized sign diagrams, one for the first derivative and one for the second derivative. So in order to achieve that goal, I have to have nice expressions for those derivatives. All right, so let's start by taking the derivative of f with the quotient rule. So the way I like to write the quotient rule is the numerator first. So it's the undifferentiated denominator times the derivative of the numerator minus the other way around. Undifferentiated numerator, derivative of denominator. And all of that has to get divided by the denominator squared, which I'm not even going to multiply out. I'm just going to leave it like that. It can't contribute to any zeros in the denominator, because that expression is never 0. All right, and then I want to simplify this thing a little bit. We can start by just multiplying out what we have in the numerator. If we do all that distribution, we would get what? 2x cubed plus 8x. And then watch that minus sign. We'd get negative 2x cubed minus a minus 8x. So that's plus 8x. The denominator is unchanged. Can't leave it behind, but I'm not really doing anything with it. And then I can kind of see in the numerator some nice stuff happens. 2x cubed showed up with the opposite signs, so it cancels. And 8x gives 16x. So this is the form of the first derivative that I'm happy with. 16x over x squared plus 4. Why am I happy with it? Well, because I can look at it and see where it's 0. The numerator dictates that. It's going to be 0 only when x is 0. And it's never undefined because the denominator can't equal 0. All right, so its sign diagram is going to have exactly one value on it. So let's write this is equal to 0 if and only if 16x is 0, if and only if x is 0. The only way a fraction is 0 is if its numerator is, and it's always defined. So it's defined for all x. So keep that in mind. I'm going to draw the sign diagrams together down below, but this is the information that we're going to need. And now we need the second derivative. Okay. So computing f double prime, again, it's a quotient rule computation. I should have already said this, but stop the video and do it without me. I'm personally looking right here when I go to take this second derivative. And it's a quotient rule, and when we differentiate the denominator, we're going to need to use the chain rule. All right, so it's getting kind of deep, but as long as you just focus on one thing at a time, these computations never really get that out of control. Okay, so quotient rule, we're going to write the denominator down. X squared plus 4 quantity squared times the derivative of the numerator, that's just 16. And then we're going to subtract the numerator undifferentiated times the derivative of the denominator. It's a chain rule problem. The derivative of that denominator is 2 times x squared plus 4 to the first power times the derivative of the inside function, which is 2x. And all of that has to get divided by x squared plus 4 squared squared. That is the fourth power of x squared plus 4. Okay, let's simplify this thing a little bit. There's some cancellation in the two terms. The numerator's terms are separated by this minus sign. Yeah, and this x squared plus 4 factor, it's in both terms. So when it's in both terms, you can cancel it. If it's only in one term in the numerator, you can't cancel it, right? It has to be present everywhere. This is equivalent to saying that if I factored out x squared plus 4 from the numerator, well, there wouldn't be any in the second term, and I'd be left with one of them in the first term, and that factoring out will cancel one of these downstairs, leaving me 3 of them. So that's what I'm going to do. All right, so you can do this algebra on your own and make sure you get the same thing. But if I factored out x squared plus 4 out of the numerator and canceled it, I'd have 3 of them left in the denominator. And this, the one that's left here would get multiplied by 16. So I would have 16 times x squared plus 16 times 4. And then on this side, I've already factored out this x squared plus 4. It's gone. So I just have to multiply 16 by x by 2 by 2x, right? So that's 16 times 4, that's 64x squared. All of that is divided by x squared plus 4 cubed. Make sure you know why it's cubed, because I canceled one of those x squared plus 4s. You can do this algebra differently. I mean, I'm trying to resist expanding everything out and then gathering terms and factoring. If I can see some cancellation along the way, I want to do that. Okay, so now in this numerator, if we factored out a 16 out of everything, then what would be left in there after we do that? I would have an x squared, a 4, and a negative 4x squared. So that's going to simplify to just 4 minus 3x squared in those parentheses, and the denominator is not doing anything. All right, and once again, I can see where that's equal to 0 and where it's not defined. It's never undefined. The denominator is never 0. So this second derivative is equal to 0. I'm going to move down to my next page. If and only if 4 minus 3x squared is equal to 0. And that's if and only if x squared is equal to 4 over 3, which is true if and only if x is plus or minus 2 over the square root of 3. All right, so those are the two numbers that make my second derivative 0. So now it's sign diagram time. Sign diagram time. I'm going to have to do a little bit of scrolling here to go back and see the details of these derivatives, but let's make a number line for f prime. And let's make a second one for f double prime. Yeah, and what are we going to mark on these things? Well, on f prime, we're going to mark any numbers that made the first derivative 0. You can scroll back in the video if you like, but I can remember that there was only one value, and it was x equals 0. On f double prime, I'm going to mark these two numbers, negative 2 over the square root of 3. It's like about negative 1.1 or so, and it's positive. Those two numbers make the second derivative 0. Okay, and now I have to fill in the signs. I have to fill in the signs. Maybe it's more convenient for me to write here. Do you guys remember? You can scroll back, but to tell me if I'm wrong, the first derivative was 16x over x squared plus 4 squared. So if you take a value of x less than 0, you take it in this interval to the left of 0, the derivative is going to be negative there, because 16 times a negative number is negative. The denominator is always a positive number. It's a square. So the signs in the sign diagram are going to look like that. Conversely, if you take a positive number, the first derivative is going to be positive. That confirms what our intuition said, that it's decreasing. What color pen am I supposed to use? This function was decreasing from negative infinity to 0, and then it started increasing. So we have a local minimum at x equals 0. And that's what that first derivative sign diagram tells us. Okay, the second derivative, it's harder to remember. Let's see if I can squeeze it in here. It was 16 times 4 minus 3x squared all over x squared plus 4 cubed. And again, that denominator is never negative. So the signs of the second derivative come only from there. Yeah, so you can pick specific values. I'm actually looking at that expression that I just highlighted in yellow and realizing that it's just the yellow expression itself is an upside down, an opening down quadratic function, a parabola. And an opening down quadratic parabola changes sign at left to right from minus to plus to minus. Okay, so this tells us about the concavity. Notice that this concavity, positive concavity at our critical value, that confirms that we have a local minimum there. Yeah, I'm going to use my second derivative test color, but it's telling me that this function is concave up at that critical value. If you're concave up at a critical value, that critical value must be a local minimum. Okay, so that's the second derivative test. So really these things encompass all of the information we need. The function's concave down, then it's concave up, and then it's concave down. And we've located the x values anyway of the places where they switch concavity. So those are the x values of our inflection points. So really, we just have to kind of summarize this stuff from this diagram. So maybe you can speed forward in the video. It's no fun to listen to me talk and write. I kind of do it slowly, but let me just kind of write down what we've got. So I've got that f is decreasing on the interval from minus infinity to 0, and it's increasing on the interval from 0 to infinity. That's by our increasing decreasing test. Okay, we have one extrema, and it's a local minimum at x equals 0. We already computed above, f of 0 is minus 1, so the local minimum value is negative 1. Okay, so that's from the first derivative sign diagram. What do we know from the second derivative? F is concave up on the interval from minus 2 over the square root of 3 to 2 over the square root of 3. And f is concave down on the interval from minus infinity to negative 2 over root 3, together with 2 over root 3 to infinity. All right, so these are the forms that I'd like you to record your answers to such questions. And then finally, we have inflection points. X equals negative 2 root 3 and x equals positive 2 over root 3 are the x coordinates of the inflection points. Sorry for the abbreviations, but I'm running out of room. And I checked before. I hope you'll check on your own that f of plus or minus 2 over the square root of 3. Stop the video and scroll back to the formula for f and compute these things yourself. But plus or minus, you'll end up getting minus 1/2. Okay, so the coordinates of the inflection points are plus minus 2 over root 3, comma, minus 1/2. All right, so let's just enjoy all of our work here. If I scroll down, I've got a nice labeled picture of this function. And you can see I've marked on there, just plotting the points in Desmos where this stuff happens. But I'll just kind of laser point and talk us through it. But sure enough, there's a local minimum at x equals 0, and that minimum value is -1. It happens to be a global minimum because it's the only extrema. The graph helps us see that. We calculated right at the outset that this thing has a horizontal asymptote with equation y equals 1. So as x goes to plus and minus infinity, the outputs of this function are approaching 1. We know that this function will never cross its horizontal asymptote. It's not forbidden to, but if this function ever rose above the horizontal asymptote y equals 1, can you imagine if the graph ever got above that line? Well, to approach the line, it would have to turn around. It would have to start decreasing. And we know that the function never decreases over there. Yeah. So this picture is sort of telling us that this is what it looks like indefinitely. The further and further you go out, the smaller and smaller this gap would be, but the picture is going to look like that. We're not missing any key information. That's always an important thing to know because you can always only look at a finite part of a graph at a time. Here I've labeled our 2 inflection points. Instead of Desmos didn't give you that 1.155. That's your 2 over square root of 3. And that's my dog. And well, that's the example.